Okay, everyone, welcome back. We're going to start our talks part now of this session. So first up is Simon Perkins from the South African Radio Astronomy Observatory. Simon is a scientific software developer there, and now he's going to tell us everything you need to know about distributed streaming radio astronomy reduction with Dask.
Anyway, thanks for the introduction. I just want to set a bit of context that in South Africa, we've got an instrument called Meerkat, and about 8 hours of Meerkat data, 4K channelization data is about 1 terabyte. And if we change to 32K data, 8 hours of Meerkat data is about 8 terabytes. So there's a strong need to be able to process data in a parallel distributed fashion. And we've been looking at a framework called Dask for doing so. So Dask is a Python parallel programming framework. And I think one of the interesting things about it is that it expresses programs as computational graphs. What are computational graphs, you might ask? Well, on the left, we've got a program containing 5 statements. But this program can be represented as a graph where A and B contain literal values and are root nodes. And we can see that node C depends on A and B to calculate its value. Similarly, node D depends on node B to compute its value, and E depends on C and D. Now, Dask would represent this as a plain Python dictionary where key value pairs define a node. So the key is usually a string or a tuple of strings and ints that uniquely identify a node, while the value can be either a literal, so a literal value, or a task. Now, tasks are characterized as being a Python tuple whose first element is a callable or a Python function. Followed by other arguments that the function should be called with. So this is a delayed representation of how a function should be called. But the other interesting characteristic about this is that the callable arguments can be other node identifiers. So we can see in the slide that the task for node C depends on summing the values of nodes A and B. So this essentially defines our program, and this program gets evaluated when the dask.get function is called. So the graph DSK is passed in, and we tell Dask that we want to get the value of node E, and it should print 9 out. So I think what's important about this representation is that it's very simple and it's very flexible. And because essentially any Python callable can be encoded as a graph task. And this means that Dask integrates very tightly with the rest of the PyData ecosystem, particularly with packages such as NumPy, SciPy, and Pandas. So we construct these graphs and then we hand them over to what are called schedulers in order to execute them. Now in this diagram, graph nodes are tasks, red nodes are currently executing tasks, while blue nodes are tasks that are complete or finished. And the thing to note about this diagram is that task dependencies induce an ordering in which tasks must be executed. And this is great because it reduces the need for distributed synchronization primitives such as locks and barriers. But we can still depend on the independence of tasks within the graph, or we can use that feature of independent tasks within the graph in order to simultaneously execute independent tasks on multiple cores or multiple nodes on a cluster. So Dask has three schedulers. The first two are single machine schedulers, where the first schedules tasks on multiple threads. The second schedules tasks on multiple Python processes. But the third scheduler is a distributed scheduler, which is quite sophisticated in that it's a server to which multiple workers connect and multiple clients connect. And the idea is that if you write a program that can be expressed as a graph, you submit that graph to the scheduler, which then decides how to schedule that work over multiple workers. And the idea is, yeah, that the scheduler will schedule graph tasks on the unit of parallelism. So low-level Dask graphs are flexible and powerful, but it would be cumbersome to express an entire program like this. So what Dask does, it provides familiar abstractions for building Dask graphs. And it does this by providing things called high-level collections, usually called Dask arrays, which I'll emphasize in this presentation. But there are also Dask data frames, which look like pandas data frames, while Dask arrays look like NumPy arrays. So they have NumPy semantics, which will provide great familiarity to the scientific programmer. So you can see in the code on the left, we're not creating, it doesn't look like we're creating graphs at all. It just looks like we're chaining NumPy-like expressions together in order to create a program. But of course, there is a low-level graph backing it, and you can see that on the right over here. The other important thing to note about Dask graphs is that they are chunked. So these arrays that we're creating, A and B, they've got 100 elements in them, but we've divided them into chunks of 5 or 20 elements each. And this is a convenient mechanism for subdividing data in order to support out-of-core compute. And it also provides data parallelism, i.e. like the idea of how many chunks of data will be processed in parallel. Dask generally tries to aim for about 100 megabytes to a gigabyte in a chunk. And it's important to note that this heavily influences the memory characteristics of your application. And generally, your largest chunk size times your unit of parallelism will give you an indication of maximum memory usage. The other thing to note about Dask arrays is that they're lazily evaluated. It's important to note that when we're using Dask arrays to construct expressions, we're merely constructing a Dask graph under the hood. So I think what I want to emphasize is that when we're creating Dask arrays, we are creating programs. A is a program on its own, but B or A and B are A, B, and C are programs on their own, but D is a program combining A, B, and C, and so D is that final program, but it's never evaluated until this compute method is called on the D array. And this is a very important property because it allows us to flexibly compose operations into streaming distributed pipelines. So with Dask as the parallel framework, we set about developing an ecosystem for developing radio astronomy applications using Dask. And one of the important components of this is dask-ms, which is a data access layer that exposes CASA tables as X-array data sets. A picture is worth 1,000 words. So what one does here is one calls XDS from MS on some measurement set, which will produce a list of data sets. I'm displaying the first one here, but one can see that this data set is a logical collection of task arrays which represent the cassette table columns in the measurement set. So you should be able to see our familiar antenna 1, antenna 2, data flag, etc. But the reason why we have a list of data sets is because Dask arrays are dense. They don't handle variably shaped data at present. And the fact is that the measurement set as a format supports variably shaped columns. So essentially we have to partition our data sets by data descriptor ID and field ID. That's our default partitioning scheme. It is possible to add others. Its capabilities, it supports reading from cassette tables or measurement sets. It supports updating and creating new ones. But I think also what I want to emphasize is because Dask arrays are programs, it also provides interoperability between the cassette table format and newer HPC formats such as ZAR, which has been supported by Xarray for about 2 or 3 years. But there's also the potential for adding Parquet and Orc support. It also supports, that can be seen in the code on the left. It's pretty easy just to reiterate over data sets from a measurement set and create a corresponding ZAR data set for use. Another important feature is that your chunking influences your memory characteristics, and dask-ms supports chunking by arbitrary dimensions. Here we've specified a chunking of 1,000 rows and 16 channels. And it's important to emphasize is that if you go too small, you'll generally have bad CPU support performance. And if you go too large, you'll tend to run out of memory. Now that we've got our data access layer, we then build algorithms on top of this. So we've got a codex-africanus algorithms library. The idea here is that one implements solutions to a chunk, like a chunk of the Dask array or a chunk of the algorithm. So for example, here I've displayed like a phase delay implementation accelerated to C++ or Fortran speeds with numba. But the idea is that one just takes in NumPy arrays, LM, UVW, and frequency, and return a NumPy arrays, i.e. the complex phase. Then the idea is that then one implements a Dask wrapper around these number functions that has exactly the same interface as the number function. So you can see this Dask phase delay function takes LM, UVW, and frequency, and it's taking these LM, UVW, and frequency arguments as Dask arrays. So we're getting programs in, and we're mapping number functions over the chunks of those Dask arrays to produce another output Dask array. So what we're doing here is we're chaining operations together in a graph to create a program. And by doing it in a chunk fashion, we support distributed programming by subdividing the problem.
Sorry to interrupt, 2 minutes left.
Okay, so then if one wrote a predict function, this is the smallest one that I could think of. Here we've got our LM component model. One iterates over the data sets, computes the phase delay, sums over the source coherencies, stack some visibilities, assign them to a data set, and write those visibilities to the cassette table. This is all lazily evaluated and only gets executed when the write function is, or the compute function is called. So this has enabled a very rich ecosystem for creating radio astronomy applications, and the following applications have ADAS posters, cortical, I won't go through them, and I'll be doing a distributed demo in about 30 minutes. Thank you, I'll take questions.
Thank you very much for your talk. You have a couple of minutes for questions. Just a reminder, if there are any technical questions, I believe in about half an hour, Simon, you are giving a demo, a focus demo on Dask. Is that correct?
Yeah, that's correct.
Yeah. So maybe so we've got a couple of technical questions. So maybe people will not be able to attend it. The first question is, can you also execute shell commands with a Python function with Dask?
I suppose one could. I've never. I think. Yeah, that's possible. I haven't used it in that context though.
Okay. The second question is not technical one, and it might start some discussion. There was a talk yesterday about heat, which allegedly outperforms Dask by an order of magnitude. Do you think that was a fair benchmark?
I have to admit, I'm not sure. I didn't see that talk, but I think it would be very important for me to go back and look at it. I know that they do compare with other frameworks like Vix. But yeah, I can't answer that question offhand.
Okay, cool. Right, there are still a couple of questions. As I said, there are technical questions. So yeah, if you could answer them on Discord, that would be great. And yeah, if anyone is interested in more details in Dask, as I said, Simon is giving a focus demo in about half an hour. So thank you very much.